Hello everyone and welcome to this session in which we will solve another problem pertaining to the topic of entropy by means of a computer. A cylinder is fitted with a frictionless piston which contains water, and the back face maintains a pressure of 10 megapascal. Initially the water is at 700 degrees Celsius, so T1 is 700 and the volume of the whole container is 100 liter. It is now cooled to saturated liquid. So what is the quantity here we have? So V total is not an independent quantity. So the quantity is actually the pressure, and it is going from this state to state 2 where it is a subcooled liquid, is saturated liquid. And so here the pressure remains constant. So P2 is 10 megapascal. The heat released during this process is now used to is now supplied to a heat engine that rejects to the ambient at 30 degrees Celsius. If the overall process is reversible, what is the net work output of the heat engine? That is the question. So let us see how we can do this. So we have P1 is equal to 10 megapascal, we have T1 is equal to 700 degrees Celsius, and VT1 is equal to 100 liters. So it is basically 0.1 meter cube. So V1 equal to volume, steam T equal to T1, P equal to P1, this gives a specific volume. So the mass is equal to the total volume divided by the specific volume, that is the mass. Okay. State 2, x2 is equal to 0, and we have P2 is equal to P1. Okay. So now Q12, which is, if I consider this particular mass as a control mass, then I can write Q12 is equal to m U2 minus U1 plus W12. But what will be W12? W12 will simply be the external pressure multiplied by the change in volume. So if I can write it in terms of the total volume, alternately I can also write it in terms of the mass multiplied by the specific volume. It is one and the same. So then let me write down Q12 is equal to mass times U2 minus U1 plus W12, where W12 is mass times V2 minus V1 times the pressure. So V2 is equal to volume, steam. We can use the pressure at state 2 and the state and the quality to find out the specific volume. So with this you also need to fetch the internal energies. So U1 equal to int energy, steam, T equal to T1 and P equal to P1. Similarly we have U2 equal to int energy, steam, P equal to P2 and X equal to X2. Is basically the internal energy of the fluid. Okay, it's completely saturated liquid. So with this we have Q12 equal to minus 5647 kilojoule. So that is heat transferred to the system. So if this was the heat, this much amount of heat would be minus 5647, which means if I draw the arrow like this, it would be 5647. So basically this particular Q is nothing but 5647. So if I draw the heat engine now, this particular heat to the heat engine basically, which is QH, is nothing but minus of Q12. Try to understand, because I have considered the control mass as H2O. The sign convention tells me that if I take it as positive, then heat is to the system. Pardon me. So that is why I have drawn the arrow like this. So the numerical value comes out to be negative, it means actually the heat is going out of the system, okay, the system is losing heat. So QH is actually, so the QH to the heat engine is actually minus of Q12. Let us just keep that in mind. So we write it over here, QH is basically minus of Q12. So now it is given that the overall process is reversible. So what is the strategy we adopt over here? We consider this, so forget about this arrow. We consider this to be the control volume. So for this particular control volume, we have some water which is changing its state from state 1 to state 2, and we have some heat rejection and some work. So the work does not contribute to the change of entropy. So if I write down delta S of the system is equal to delta S of water plus delta S because of the heat transfer. So this, let us include, because we have been given that the overall process is reversible, we have to also include the heat transfer to the ambient, delta S of the surrounding. Okay. So what do we have? So delta S of the water is mass times S2 minus S1. And what is the entropy change of the surrounding? It will be equal to minus of QL by the T ambient in Kelvin as per the sign convention. So we write here, and this overall is obviously 0. Okay. So then we have mass times S2 minus S1 minus of QL by T ambient, which is basically 303.16 Kelvin, is equal to 0. Okay. So let us see what QL we obtain. So we have forgotten to fetch the properties of the property entropy. S1 is this, S2 equal to entropy, steam P equal to P2, X equal to X2. So let us see what QL is. So QL as per this equation is minus 2649 kilojoule. Okay. So this was the ambient. If the ambient is absorbing an amount of heat QL, then the surrounding is losing an amount of heat minus QL. So this is that QL over here. Okay. So this is the heat, this QL is the heat going into the system. Because QL is negative, it means that this sign, this arrow is actually correct. But anyway, this is the sign convention that we have used to evaluate this evaluate this particular equation. Okay. This, as we have discussed several times in the previous problems, this is the delta S of the total system when QL is positive. Okay. Moreover, QH is like this. So then what is W? So as per the sign convention, QH and QL are both positive, and W will then simply be QH plus QL. So W comes out to be 2999 kilojoule. So that is the answer. So in this in both of the problems that we discussed a few moments ago, and this particular problem, one has to be very careful about what control mass, what control volume you are choosing. For one control volume, if the heat absorbed is positive, then obviously for the other control volume it is losing that amount of heat, maybe. So in this particular case, this control mass was losing an amount of heat QH, but that amount of heat lost is gained by the heat engine, hence we had this particular equation. Okay. Then if for this entire control volume we had some amount of heat entering into the control volume QL, then the reservoir is actually losing an amount of heat. So the reservoir has a heat transfer of minus QL, which is appearing in the entropy equation. So minus QL by T ambient is the delta S for the surrounding. This is the entropy change for the system, m into S2 minus S1. So combining this, we have delta S of the system, which is 0, because the overall process is said to be reversible. There is no entropy generation in the entire process. The entire process is free of any entropy generation, and hence we could find out what this final heat transfer should be. See, because in this particular control volume, okay, the only interactions are heat and work. This thing is internal and hence it does not figure. Whatever is there inside the control volume is only water, it is changing state from 1 to 2. So the change in entropy of water is known, because entropy is a state property. We do not need to bother how that water went. It is a constant pressure process, we do not need to really bother about that. As soon as I know states 1 and 2, I know what the change in entropy of the water is. Now because there is a heat interaction with the ambient, this particular sign means if the system is absorbing an amount of it QL, then the reservoir is losing an amount of it minus QL. Hence it comes over here. That gave us QL, and once that is known, I can now take only this thing as the control volume, the heat engine. So for the heat engine you have QH going into the system, which is basically minus of Q1, because of the reasons we just discussed, that heat lost by the mass is heat gained by the heat engine. So because of this, QH is like this, QL we just found out using the sign convention as like this, minus 2649, and thus if we consider the heat engine as the control volume, the work is nothing but QH plus QL, and that is what we did. Please do this problem on your own, try to understand which control volumes to analyze. Here we analyzed H2O first, the whole system plus surrounding second, and then the heat engine third. Using this we were able to find out the work output of this particular heat engine. This is the work done by the system, because as per convention work is coming out of this control volume. Okay, work is coming out of this control volume. So with this we stop here, we conclude this particular example, and I hope you will go through similar problems and try to have an intuition of which control mass, control volume to take to solve the various problems. It is all very conceptual, there is nothing fantastical about this. The problem has to be first conceptualized, and then you can just fetch the values. It does not matter how you fetch the values, you can use a table, you can use a computer. The computer is very convenient because you do not have to interpolate, you don't have to think about what the values will be. So with this we conclude this session, and I will be back next time with another question. Thank you.